So, believe it or not, we're still not done with this idea of which direction do reactions go. And that's because it's complex and it's also really important. So, we want to make sure we fully understand it. Let me just reiterate the delta G naught prime is the standard free energy change for a reaction. And that is based on the difference between the stability or potential energy of the substrates and the products. For the case of the hydrolysis of ATP to ADP and phosphate, it's a downhill reaction, and therefore it's favorable or has a propensity to go in the forward direction. It's the opposite down here where we have glucose and phosphate becoming glucose 6 phosphate. It's an uphill reaction. It's not favorable in the forward direction. It has a propensity to go backwards. Now, here's the important part. What if we need these reactions to go in a way that their propensity is not inclined? For instance, what if we need glucose to become phosphorylated on the sixth position? In fact, in the next chapter, we're going to find out that's exactly what we do with glucose that we eat. We put a phosphate on it in the sixth position. So if it's an uphill reaction, how does that happen? What if we wanted to take ADP and phosphate and make ATP? We do that all the time in most cells in your body, constantly. How do we do that if it's an uphill battle? In fact, it's a big uphill battle. Well, there's two different ways we can make uphill reactions go. And the first way is by what we call Le Chatelier's principle. And you may have learned this in other classes, but we'll go over it from scratch right here. Let's consider a reaction A plus B goes to C plus D. If it's at equilibrium, then that means the concentrations of A, B, C, and D are going to stay the same. What if we want it to go in the forward direction, though? Le Chatelier's principle tells us the answers. And here's how it works. If we increase substrates, we would increase the concentration of either A or B or both, or we decrease the products, that is C and D, then we shift toward product. That is, we shift in the forward direction, even if it's an uphill battle. So let's make a note of that. It's like you're increasing A and B and they overflow and flow towards C and D. The opposite can be said of the reverse reaction. If we decrease substrates or increase products, we can do the very opposite thing. If we increase C and D, we end up overflowing those and they shift backwards to reestablish the equilibrium. That means they shift toward substrates. That's what Le Chatelier's principle is. And just to say it again, if we have a reaction like glucose plus phosphate going uphill to glucose 6 phosphate, normally the reaction would accumulate over here where there's glucose and phosphate. And that's just like water pooling in a valley instead of in a hill. And if it pools over here at equilibrium, as long as we can increase the reactants or decrease the products, it's going to flow uphill to reestablish that ratio that we have at equilibrium. We can do the same for a backwards reaction, like this one here. Normally, we said that at equilibrium, the products would pool 420 to 1 of the substrates. So how do we go back uphill? Well, we'd have to increase it beyond 420 to 1, and theoretically, it could go up. Now that's Le Chatelier's principle, and we're done with it. But since this is a short video, I want to remind you of one important thing. What we're talking about right now is the favorability of reactions, and that's going to be based on the comparison of the energy of the substrates and the products. Like we said, downhill in this case, uphill in this one. There's a whole different issue that we need to remind you of from a previous chapter. The fact that the hill is very large here means it's going to go to equilibrium very, very slow. Same thing down here. So no matter what we think about whether it's going to go downhill or uphill, in this case, it's going to go very slow because there's a huge hill in there. Now we can make it approach the equilibrium, whatever that equilibrium is, faster by lowering that hill. Do you remember how we lower the hill? It has nothing to do with adding substrate or product, and it has nothing to do with the relative energies of substrate and product. Maybe you remember. The only way you can lower the hill is to add an enzyme. I want to just finish this video by reminding you of something we said way back in our enzyme chapters. Enzymes lower this activation energy. That means they make the reaction go forward faster and backwards faster. But enzymes do not change the overall difference between substrate and product reaction. That is, they don't change the delta G naught prime. So an enzyme cannot make something favorable or less favorable. It can only make it achieve where it wants to go at equilibrium faster. That's an important difference, and we need to keep it in context here. Okay, that's our first way to make reactions move in a direction they may not want to go, Le Chatelier's principle. The next one is probably even more important, and we're going to cover it on the next video.